everyone, and welcome back to the next session of the A4Q Testing Summit. Next up is Fabian Streitel from Germany with the topic, everyone wants to shift left, but our tests are just too slow. Hi, Fabian. How are you doing?
Hi, great. Looking forward to the presentation.
Okay, perfect. I'm happy to hear that. Let me just introduce you real quick before we dive right into it. So you are a software quality expert and team lead at CQSE, where you help companies optimize their testing processes using the TeamScale platform, drawing on years of experience across diverse industries. So you've been in the industry for quite some time, and therefore we are very grateful that you share your experience and your knowledge with us today. I just want to say for all the people who are watching us at the moment, I want to encourage you, please ask questions, leave comments. We have a Q&A part at the end. So the more questions you ask, the more answers you will get. So yeah, feel free to leave as much comments as you like. And of course, there will be a voting, as you maybe heard several times now already. There will be a voting for best speaker and best presentation. So don't forget to vote for Fabian if you like his presentation, which I think you will. So Fabian, I don't want to let the people wait any longer. So the stage is yours. Have fun, have a great presentation, and see you later at the Q&A part.
Thank you, Michael. All right, my name is Fabian Streitel, and today I will show you two approaches how you can shift left even if you have a really slow test suite. As testers, we are in a dilemma because on the one hand, successful software grows. So this means we rarely remove features from our software. We usually only add more features, and that means there's ever more code to test. On the other hand, release cycles are getting shorter and shorter, and this means there's less and less time to do the actual testing. And in this dilemma, we are under a lot of pressure to do our tests more efficiently and more effectively. Shift left is one paradigm that seems like a solution to this, where we try to have our testing intertwined with development, to be testing early in the development lifecycle and give feedback about new bugs more frequently. But if your test suites, like many of the test suites from my customers, run for hours, maybe days, or even weeks, then it seems unattainable to shift all of that testing to the left. But there is research on this subject, and I'm going to show you two approaches from research today that actually help testers do this shift left, even if you have really slow test suites, and that are not just looking good on paper, but actually work in practice, even if you have complex test suites, if it's a legacy project, if it's been around for a long time, or if it uses really legacy technology. Before we get into that, a little bit about myself. I'm a team lead at CQSE, as Michael already mentioned. And disclaimer up front, we make this tool called TeamScale, which implements these analyses. But the focus today is really on the research results. And you can, of course, also implement these techniques without our tool. As a team lead at CQSE, I basically wear two hats. One is the research hat, where I supervise bachelor and master theses, where students look into new approaches, how we can help testers test more efficiently and more effectively. But the other hat is the practical hat. I've also been working for the past 7 years in customer projects, implementing these approaches to make sure that what we're looking at in research does not just look good on paper and work in theory, but is actually transferable to industry projects. Because unfortunately, a lot of the research results seem really fine, but then in the end turn out not to work in practice because, for example, they rely on data that we don't have available, or they rely on preconditions that just can't be satisfied in an industry context. So the approaches shown today, they have gone through both sieves here. So they are valid research results and they work in practice. When I talk to my customers, many of them have invested a lot in automation in the past few years. So their automated test suites have grown, but a lot of them also test manually, and manual tests play a big role there as well. So many of them also have large manual test suites. And the longer a software project has been around, the more tests have been added to these test suites. And this means that they are usually not test suites that run within minutes and give fast feedback, but rather they are rather slow and take hours or even days to run. To give you some examples, Bayerische Versorgungskammer is one of my customers. They are doing an insurance system, and the nightly end-to-end tests run for 12 hours at the moment, which is just about short enough to still be able to run it at night. But if we think 3, 4, 5 years in the future, they will probably add more test cases, and then it will turn into something like a weekly test. On the other end of the scale, I have, for example, BMW as a customer, where hardware in the loop tests, where they test these hardware devices that go in the car, they can take up to 4 weeks for all the end-to-end tests to complete. And you can imagine that these long test run times are painfully slow, because if I, as a developer, check in a bug, and then only 4 weeks later I find out that the check-in that I made actually contained this bug and broke something, then by that time I've probably forgotten what I've done. And it's also not clear which of the many changes that went into that test phase actually caused the problem. So there's a lot of additional effort that we get simply because these test suites are so slow. And it would be much nicer if we could take all of these valuable tests and run them more frequently and early in the development lifecycle, so we can give this feedback faster to development. But it seems rather unattainable when these test suites take so long. So there is a lot of research on this topic to see what kind of approaches can be used to solve this conundrum. And there is a very simple idea that actually works in practice that is called test selection. The idea here is, instead of taking this large test suite and running it very infrequently, why don't we take a subset of the test suite that is much faster? So let's say a few tests that only take a few minutes to run instead of hours, and then run this much more frequently. Of course, this can only work if this subset can proportionally find much more bugs than the average of the whole test suite. So we need to have a lot of bug finding power concentrated in a few tests. And there's a lot of research on different approaches that we can use to achieve this. And not all of them can be transferred to practical implementations, because, as I said, some of them rely on data that we don't have available or on preconditions that we can't satisfy. But the two that I'll show today, they actually work really well, even in large legacy projects. Let's go a little bit more into this idea of test selection. So imagine this is your test suite. Every rectangle here represents one test, and the green sort of signifies they do different things in the system. Now, when you run all of your tests, some of them will find bugs, meaning they fail, indicated by the red X. One critical insight here, usually there's not a one-to-one correspondence between a test failure and a bug. So for example, in this case, there's only 3 bugs, but much more test cases that fail, because usually one bug causes more than one test case to fail. So the color of the bugs here indicates that there are different bugs. Now, when we make a selection from this large test suite, so let's say we only run the tests on the left and not the tests on the right, then this helps us, because now we don't need to have every single test failure represented in the selection. So for example, for the orange bug, it's enough if we have this one test failure in our selection, then we can still start to debug that bug and get rid of it, and that will of course also solve the other failures that are caused by the same bug. So that helps us. Another key insight, these techniques that I'm showing today, they give us no guarantee that all of the bugs will in the end be represented in the test selection. And you can see this in this example for the purple bug. This has not made it into our selection, so this selection would not find the purple bug. But for our intended use case of finding most bugs faster, this is not a problem. So let's look at what using such a smart selection would look like in practice. This is sort of representing the situation that most of you will probably have at the moment, where you have one main branch and you infrequently run your complete test suite on the main branch. Let's say once a day, once a week, whatever cycle you have. And in between, a lot of changes are coming into the branch that are getting tested with the next test run. Now, if we have this smart selection and it works really well, then what we can do is we can run this small test suite that, for example, takes only a few minutes much more frequently, both on our main branch or even on something like a feature branch. And this will help us find most of the bugs much earlier. Usually what we aim for here is sort of a Pareto distribution where we can find 80% of the bugs with 20% of the test time. And then this will allow us to shift most of the bugs to the left. Of course, as with the purple bug, some of the bugs will not be found by the smart selection, but that's not really a problem. We'll still find them in the interval that we find bugs today, which is these complete test runs that we still keep doing to make sure nothing really slips through. But most of the bugs will be found much earlier, and this helps us really intertwine our testing more with development and be faster and allow these shorter release cycles. Now, as you can imagine, it all hinges on this selection to put a lot of bug finding power into a small set of tests. And the two approaches that I showed today, they use different properties of test suites to achieve this concentration of bug finding power. And the first approach does this by using redundancy in the tests. And to be able to show you what I mean by that, I have to introduce a visualization here. This is called a tree map. What this is basically a representation of a software system as a 2D graphic. So it's sort of like a map of your software system. Every big rectangle that you see here, surrounded by these white lines, is one component in the software system. So in this case, this is 1 million lines of C# code from an insurance system. You can see there's some components for UI stuff and some for authentication and so on. The more lines of code in a component, the bigger the rectangle. And what I'm going to do is I'm going to step by step go into these components. So now we have all the classes in each component. And inside the classes, I can now draw all the methods. And now still the more lines of code in a method, the bigger the rectangle. What I can do is I can use color to represent what we know about all of these methods. So for example, test coverage. Which of these methods are getting executed as we run our tests? So all the green methods, they have been executed while the tests were running. All of the gray methods, they don't have any tests. And what I can do with that is I can show you this redundancy in a visual way. So what we usually see with these large end-to-end test suites that run for hours, days, weeks, is that when they were written, there was a lot of copy pasting. So to make a new test case, people usually take an existing test case and make minor adjustments. And then they get a new test case. But both of these test cases roughly do the same thing with only this minor variation. And if you look hard enough, I'm not 100% sure how easy this is to see via the stream, then, for example, the top row, all of the test cases have roughly the same test coverage. Now, when we make a selection of our tests, of course, it would not be a good idea to, for example, just take the top row, because then we're only focusing on a very narrow part of our application and we could only find bugs in that area. Rather, it would make much more sense to take very diverse test cases to make sure that we're testing all across the application. So basically, we want to get rid of that redundancy. To show this in another way, this is from an industry system. And what you can see here is the runtime of the test suite on the bottom, from 0 seconds when we start the test suite to 6 days when it's finally done. These are hardware-in-the-loop tests for a medical device. And then on the other axis, you can see after running a few tests, how much test coverage have I achieved, where 100% means all the test coverage that the test suite can possibly achieve if you run all the tests. And what you can, of course, also see is these plateaus here. This is the redundancy. So basically here we're running a lot of tests in a row that all do pretty much the same thing with only minor variations. And so they're not really covering much of the system. And now again, if we want to make a selection, it wouldn't make sense to take, for example, the first 5% here, because then we would only cover 15% of the whole software system. Rather, if we reorder these tests and take the most different tests to the front, so basically the ones that make these large jumps in coverage here, then we get a curve like this. And if we cut off now, then you can see with just 5% of the test suite, we would in this case achieve almost 100% of the test coverage that the entire test suite can achieve. So we're really going over the whole system, and now we have bug finding power for the whole system in this small test suite. And this is the first approach, is trying to use this dissimilarity between tests. And of course, there's a big bunch of different ideas of how you can measure similarity between tests. Test coverage is one thing. You could think about how many characters are in a test in the test case, what kind of concepts does it talk about, and so on. So there's lots of different measures of test of similarity. We tried a bunch of them in different research papers and came out with one that works really well. But regardless of what metric you use to judge this similarity between test cases, this is basically a clustering problem. What do I mean by that? What all these metrics do is they put all of our test cases in a vector space. So basically every circle here represents one test case. And if these metrics work well, then they cluster similar test cases together. So all of these test cases here would be doing very similar things, and all of these test cases here would be doing very similar things, and so on. And they do this by basically assigning a bunch of numbers to each test case. This is a very simplified example because with 2 numbers, I can still put it on a 2D slide. In reality, we get a much larger vector space with many more entries here. But you get the idea. Now, what we can do when we have this clustering is we can take any test case as a starting point and then always pick the test that is furthest away from the ones we've already picked. So in this case, this would be the next test we pick, and then this one is furthest away from the first 2, and this one is furthest away from the other 3. And then this way we get very dissimilar tests in our list. And we can do this until we have enough test cases for the test runtime that we want to spend for our smart selection run. So let's say you want to spend 15 minutes, then you just pick test cases until the 15 minutes are full. Now, I said we tried a lot of different metrics. The one that actually worked the best and is easy to implement in existing systems actually uses AI, but maybe not in the way that you think, because we only really use the first step that every one of these large language models like ChatGPT does when you feed it some text. Again, a very simple example. What they do is if you feed it a text that contains, for example, the word man, then it turns it into a vector with a bunch of numbers. And these numbers represent how much man in the context of the text that it's in represents some of the properties, the categories that the AI learned during its learning process. So in this example, for example, does this have something to do with human or with gender or with royalty and so on? And of course, this is just a small example. In reality, these vectors have hundreds of entries, and we don't even know what the categories are that these numbers represent, because these are just properties that come out of the learning process. These are not given to the AI before the learning starts. But the good thing is we don't need to know exactly what these numbers represent. What we just need is that similar concepts are clustered close together. And this actually happens in these embeddings. So you can see it again here in a very simple 2D representation where man and woman are grouped together and king and queen are grouped together because they're conceptually sort of similar in this text. And we can do this not just for single words, but these AIs can, of course, also do it for a whole text. So we get an embedding like this for our whole test case, and then similar test cases get similar embedding vectors. And then we can use this in the approach that I just showed to pick the most dissimilar test cases. Now, when we do this, we want to know how well does it actually work. So in these papers that I showed before, we tried this both on open source systems, but also on industry systems to make sure that it actually works in practice with real world applications and not just toy examples. And on average, to find 90% of the bugs that the whole test suite can find, we need about 13% of the test runtime. So you take 13% of your test cases and run those, and you find 90% of the bugs. That's a pretty good trade-off. And that is actually enough to turn, for example, the nightly test at Bayerische Versorgungskammer into a test that they can run multiple times during the day and give feedback faster with that. And find 90% of the bugs during the day instead of only the next day. So this is already great, and a lot of teams can make use of this approach. But there are some teams where the test suites are even slower, where it's maybe a weekly test already, and 13% is still too much to give really fast feedback. So for this, we have another approach that is even more powerful. Now, to be more powerful, we need to feed more data into this approach. So the second approach does not just use the redundancy in the test cases, it also looks at what actually changed to make a change-based selection. So this means, unlike this approach where I just run the approach and I get a list of tests and they are very dissimilar, and then I can run this regardless of what changed, the next approach will select different tests depending on what actually changed in the software system. To show you how that works, I have one code change here. So this is from our own software team scale, and it shows you all of the methods that were changed when we implemented a new feature. And in this case, since we are making a program analysis tool, we have to be able to parse the programming languages that we support. So this would be a change for the programming language Java to support a new version of Java. So support for the new keywords and the new language features. And all of the colored code was changed in some way. Now what I'm going to do is I'm going to start a video where we, in time lapse, see all of our end-to-end tests running and making the areas green that they cover. So first, whenever a test runs, it turns the rectangles to white where it covers, and then they slowly fade to green. So this is 30 tests per second, and you can see how the tests sort of go all over the software system. But if you look really closely, you can see that most of the tests don't actually run through our code changes. So they have nothing to do with the changes that were made, which is also not very surprising because nobody really wrote tests for a new language version in advance because nobody knew that that version would be coming, right? So we're not having any particular tests for those changes. And in fact, of the 5,000 tests that we had at the time, only 4 actually ran through those code changes. Not 4,000, just 4. So that's a lot of test runtime that we're wasting here on tests that cannot find any new bugs because they're not running through these code changes. And we can use this additional information to make an even smaller selection that still finds a lot of the bugs. Now, what we need for that is a link between code changes that happened and the tests that relate to that changed functionality. So let's imagine you have a user story or a pull request or a release that you want to test, and we know what changed in here. How do we know that? The simple answer is from the version control system. So whenever developers check in code, they do it in the version control system, and from there we know exactly which lines of codes changed and how did they change. So an automated approach can take this information and, for example, gather all of the code changes for a pull request, and then try to find tests that match well with those changes. So in this example, let's say we changed something about login and accounting and search in some business information system. Then we can now search for test cases that deal with login, accounting, and search. So basically, this is a search problem. And search problems are, again, very well researched. Just think of Google, how many years of research went into that. So if Google can index the whole web and find relevant results for your search query, then why can't we index your test cases and find relevant results for a code change? How does this work? All of these search problems basically look like this. On the left hand, we take the things we want to index. So in this case, for manual tests, your test steps, and for automated tests, your test code. We index this into a database, and then whenever a code change occurs, we run a search query based on that code change. So we extract keywords from the code change, something like search and login and list and user and so on. And we search in the database for test cases that look similar to that search query. We call this similarity scoring. What this outputs is similar to a query on Google, a long list of test cases that have something to do with that search query, with that code change, but ordered with the most relevant tests at the top. So for a tester, what this feels like is basically like this. You at the top enter, I want test cases for my feature, or I want test cases for my pull request. The automated approach can figure out which code changes those are, extract those keywords, and give you a sorted list of test cases with the most relevant ones at the top. And as with a Google search, once you're on page 10, you're probably not going to find what you're looking for. It's the same here. Since the relevant ones are at the top, we can just cut off depending on how much test budget we want to spend. So we're looking at pages 1, 2, and 3, for example, and we say, hey, let's spend 15 minutes on testing, and then you just take test cases from the top until the 15 minutes are full. And then you have a really good chance that the most relevant tests are in that list. To illustrate this a little bit, I have one example. This is from an open source system where it's easy to show. It's called DigiBank, and you can imagine it's like online banking made in open source. So you can play bank, and of course there's accounts, and you can transfer money from one account to the other. That's what this function here does. And if we look at that function, let's pretend that we changed this function. Then from this context of the function, we can take the keywords. So I've highlighted 3 to make the example: transfer, accounts, and amount. And now I'm going to go through the different test stages and show you that in these test stages, these reoccur. So for example, a typical unit test, you need to create an account, you need to set an amount, and then you need to call the function. So obviously these keywords are in there. But also as we move up the hierarchy of the tests to more end-to-end tests, let's say we have a cucumber test that describes the use case, then of course these keywords are in there as well. A robot test that automates something via the UI, or even a manual test where we just describe what the tester should be doing, contains these keywords. So we can use these keywords to make this match between test cases and changed code. Now, of course, not every keyword is created equal. So something like public void is probably not going to help us find good manual test cases to match this code change. Or on the other side, something like in and the are probably also not good indications that this test case is related to the code change. So we need approaches that differentiate between the value of the different keywords. And this is where all of the search research comes in, and where we can learn a lot from how Google does this. And we tried, again, in a lot of studies, different approaches. And the one that works the best is one that is actually very well known in the search research community. It's called term frequency inverse document frequency. And what we want to do here is basically reward the test cases that contain our search terms a lot. This is the first part. So how often does the term appear in this test? But at the same time, we want to disincentivize those words like in and the and public and void that appear in basically in a lot of the test cases. So if a search term appears in most of the test cases, it gets penalized. And of course, this is a bit simplified to be able to fit all of this into the presentation, but together, this gives us really good results. So in this case, we now only need 4% of the test runtime to find 90% of the bugs. And you can imagine how this can now even turn a weekly test into something that you can run a few times a day and really shift left those expensive tests. All right, those were the 2 approaches. To sum it up, we have 2 different approaches. They differ in precision, but also in effort. So the AI test clustering, you have the same test suite all the time, so it's very easy to implement. The similarity scoring is change-based, so you need to have a different test suite depending on what changed, but it also gives you a lot more power. So what we usually recommend that teams do is they start on the left and try out the AI test clustering. If that is not powerful enough for your test suite, we can move to the more complex similarity scoring. And Sometimes, very seldomly, we have customers where even that is not enough. Then there's even more complicated approaches from research that we can use, for example, that use test coverage to get even more out of there. But most teams should be fine with these two approaches. Of course, you don't have to use them in isolation. You can also combine the approaches. So this would be one example as the final picture here, where we shift left both with the AI test clustering on the main branch, sort of as a quality gate when new things are merged, that they're not breaking anything across the system, and the similarity scoring on the feature branches, where we want to give the fastest feedback possible, and thus we want the 4% instead of the 13%. So, and of course, what strategy makes most sense for your project really depends on your context, your constraints, and how painful your test suite is at the moment. So if you want to talk about this, contact me. I'm happy to go a little bit more into your particular context to figure out which of these approaches makes most sense for your team. So thank you very much for listening in, and I would hand it over to Michael for the questions.
Okay, thank you very much. That was very insightful. That is, yeah, that looks like, or it sounded like it's a lot about efficiency, and you found very interesting approaches to be much more efficient. So we have the first question here. Let me see here. No new TC for new language. What is, I think that stands for test case. Yep. No new test case for new language. What is the reason to run the test suite anyhow?
Thank you for the question. So I think this refers back to the slide where I showed how the tests are not running through our recent code changes. And I think this is an interesting observation that you're making here. So of course, after we wrote the feature, we made some new test cases for this new feature, but the tests that I showed were the regression tests. And this is usually where we apply this sort of speed up, because the regression test suites, they just keep growing over time as we add new features, because we keep adding the feature tests back into the regression test suite, and then they become painfully slow. But of course, it makes sense to also run new tests that you wrote specifically for the feature, but this is really orthogonal to these approaches. You can always just do this. Thanks for the question.
Okay, I hope this question was answered. Okay, we got another comment on that. Regression needs to be maintained also.
Yes, exactly. I mean, maintenance of the test suites is another big problem area. The bigger they get, the more you need to spend to maintain these. So there's also actually a lot of research into how can we minimize these test suites. So can we throw away some of the tests, but lose very little bug finding power? Not part of this presentation, but if you're interested in that, come talk to me afterwards.
Okay. Let's see. We are streaming on so many different platforms, so I have to check. Okay, there is another one here. Is this more applicable to unit tests or also higher level tests like integration or end-to-end?
Thank you for the question. So the pain is usually not in the unit tests, because at least with the teams that I work with, the unit tests usually run within a few minutes. So there's really not much potential to optimize anything in there. So this is really more targeted towards the higher level, the end-to-end tests, maybe hardware in the loop tests, if you have those that really run for a long time. This is where these approaches shine.
Okay, thanks for the answer. Let me see here. Can we use the keyword approach also with requirements as input?
Yeah, I think if I get the question right, that actually makes sense. So I think what you mean is, can we not just match between code changes and the tests, but can we also match between other artifacts in the tests, like requirements? So let's say you haven't even implemented the requirement yet, but you want to know, do we already have relevant test cases for what is to be implemented? Then of course we can also look for keywords in the requirements and match that to keywords in the test cases to find which test cases are likely to test the new requirement. So this could be used, I guess, in a sort of planning phase as well, to see how many test cases do we already have out of our large regression catalog that would be helpful for this new feature, and what kind of test cases might still be missing. Yeah. Okay. I haven't tried this yet, but it sounds interesting.
Okay. Next question. What about typos in the test cases? Will this cause problems?
Also a very good question. So usually what we see is that what the typos are in these test suites is if we're talking about manual test cases. Now, I mean, in code-based tests, there's usually no typos because the compiler would catch those. But if we're talking about manual test cases, you could have typos about things that are in the UI or something like that. What we also observe is that usually this is not a problem in practice because there's not so many typos that it will screw up the approach. So, I mean, these AI approaches anyways are rather resistant to typos because the AI is trained on data that contains typos, so it can to some degree automatically compensate. And the keyword-based approach usually has a lot of additional keywords to select from so that the matching still works very well, even if there are a few typos.
Okay. Next question. Will these approaches also work with manual tests?
Yes, maybe that question was from the beginning of the talk. All of these approaches also work with manual tests. I mean, the AI approaches are trained on both code and natural language text, so they can understand both and they generate embeddings really well for both types of text, so code and natural language text as you would have in manual tests. So the AI approach works really well automatically. And the keyword-based approach also works for manual tests because we usually have still a lot of keywords that you can match from the manual description back to the code. Like identifiers from the UI are going to be in the code and in the manual test, and also like central words that are important for the application, like, I don't know, temperature sensor or something like that will probably also appear in both the code and the manual test. So that allows us to do the matching.
Okay, and I guess, I mean, this is all integrated in the TeamScale platform, but I guess you can use those approaches also, or those techniques also with other tools, and can implement that in your day-to-day testing life.
Yeah, of course. I mean, I'm here to talk about the research, so all of the papers are freely available, and if you want to have a look at those, just email me or talk to me, then you can implement it yourself, and we offer it in the tool. I think it's like with issue tracking or something like that. You can do it yourself, but should you do it? I don't know.
Okay.
But I'm biased. I make the tool, so
yeah, that's what I meant. Yeah. Okay, so are there any more questions? It seems like everything was pretty clear. So at the moment, I don't see any more questions, and we are also at almost at the end of our time. So yeah, maybe just one more hint. As you all know by now, I guess, there is the voting for the best speaker and the best presentation. So I think it would be a great idea to vote for Fabian here, if you enjoyed his presentation. And yeah, also, as you know, there are a lot of other presentations throughout the whole day. I mean, yeah, there are still some more to come. So yeah, I hope you enjoy the rest of the summit as well. Fabian, thank you so much again. Is there anything else that you want to add?
Well, thanks for having me, and I wish everyone a great rest of the conference.
Thank you so much. Yeah, we're very glad that we had you. Let's see. Yeah, we just get some very positive feedback here. So thank you very much. It was great to have you. We really liked the insights and those, the research results. I think, yeah, since efficiency is always a big thing, that could be very interesting for a lot of people. So thanks for the insights. Thanks for your time. And yeah, see you next year, hopefully.
Yeah, see you then.
Software testers. Move beyond theory and master testing with the AI-powered ISTQB add-on practical tester by A4Q program. The ISTQB Add-on Practical Tester by A4Q equips you with the theoretical skills and practical competence to truly excel. Learn how to apply black box testing like a pro. Estimate accurately, write flawless defect reports, and catch issues early. The ISTQB Add-on Practical Tester by A4Q complements your ISTQB certification by turning knowledge into powerful action. Visit our websites and find out more information.